magnetic force, I have to make a very sad admission. You know, one of the things students complained about last semester was me having the wrong answer on the test. I calculated one of the problems using K equals 9.987 times, well, 9.976 times 10 to the 9th. And so that gave me an answer that was 16.4. I don't remember what it was, when it should have been 17.3. So it was on one of the middle section, the application ones. No one asked me about it. I worked it out really carefully, but obviously that digit makes a difference. And so I will have to try to figure out how best to handle that again. And I just have to apologize. You know, you make your mistakes and go forward as best you can. So I'm sorry about making that mistake. What was that? I didn't hear. Yeah, yesterday's test, yeah. I've got to figure it out. I haven't even seen I looked at anyone's test to see what people have done with it. I've got to figure out what happened before I, if everybody just wrote down, I got 16.4, 17.3 is the closest, well, then we'll be great. I have to look at what people have in their test before I decide for sure how I can handle this best. Okay. I had this slide last class period, how to solve magnetic force problems. And so we have just some simple steps here. Determine if the magnetic force is zero is the first step. So we have the cases that would make it zero, if the current's zero, if the magnetic field's zero, or if the current's in the same direction as the magnetic field. Otherwise, you need to determine the angle between the length of the magnetic field, and then you find the magnitude with this equation and the direction with the right-hand rule. So let's go straight to doing a problem. A 125-meter long power line is horizontal and carries a current of 2,500 amps toward the south. So you can see here the picture has north and south identify the direction of the current. And the Earth's magnetic field is 0.52 millitesla toward the north and inclined 62 degrees below the horizon. So I have my angle, I've got what I need. What is the magnetic force on the power line? And ignore any drooping of the wire, assume it's a straight wire. What is the equation that is going to help us find the magnetic force? Force is equal to, we don't have speed here, we have current. So the equation that has current, the one that was on the preceding page, oh, is that what you said? I thought I heard something different. Okay, the current is, or the force is IL cross B. So as we saw in the previous slide, we break this into two steps. Number one is what is the magnitude, and number two, what is the direction? Magnitude is ILB, sine of the angle between the two. So in this problem, we can put our numbers right in. I was 2,500 amps. The length was 125 meters. The magnetic field is 0.052 millitesla, so times 10 to the minus 3. And then sine of the angle between the two. What is the angle between the current and the magnetic field? It's what? Okay, so you set 62 degrees. It turns out it's actually 180 degrees minus 62, which would be 118 degrees. But sine of 62 and sine of 118 are going to be the same thing, because sine is symmetric about 90 degrees. That sine of 90 minus x is equal to sine of 90 plus x. So you could actually use the 62 degrees And so just for grins, what is that number? How much? Okay, 14.34 newtons. How many significant digits do I have in that answer? Just 2. So 14 newtons. Now for the direction. How do I find the direction of the force? And this time I'll go to James because I've done Michaela and Brandon. James, how do I find the direction of this force? Not sum the vectors. I have to use the right-hand rule because I have a cross product. Remember, cross product is multiplying just the perpendicular parts, and its direction is the direction you get when you apply the right-hand rule. The right-hand rule is always which element in this. We'll start with that. So we have 3 vectors: force, length, and magnetic field. Which one of those is the index finger? I'm going to go in order. How many people say force is the index finger? How many people say length is the index finger? Yeah. 6 there. How many say magnetic field is the index finger? Okay, I have 2. 6 and 2 is 8. That means 12 of you need to learn this before the next test. So, any cross product, the index finger is the first item in the cross product. So my cross product is L cross B. So the first item in the cross product is L, so my index finger is L. So my index finger needs to point the direction of L. L is kind of the made-up vector because we can't call I the vector. So my index finger needs to point that direction. So we start with our index finger pointing that direction, and then which one is the middle finger? The second item in the cross product, B, is the middle finger. So now I need to keep my hand so the index finger is pointing that direction, but orient it so I can point my middle finger in the direction of B. So I've got to orient it like this so I can put my middle finger in the direction of B. And then my thumb is pointing the direction of the force. So what direction is the force? My thumb is not pointing into the page. My thumb is pointing out. And so the force is coming out this way. Or since this is north and that's south, if we're looking down from above, east would be coming out, so it would be in the easterly direction. Had to do it again just to double check. So we're able to find the direction using the right-hand rule and the magnitude using the simplified form of the equation. Whoops, I actually wrote it in green there. So that's a simple kind of problem. I say a simple kind of problem because there really wasn't any thought involved. It was, do you understand how a cross product works? So now we're going to move to something a little more interesting. What direction is the net force on this loop? Now, this loop actually is showing the direction of the forces. You have a wire with current going this way, this way. Okay, change color to red. Current goes as shown. What direction is the net force in this loop? Still waiting on 4 people. Okay, I'll give another 5 seconds here. We got to move on. Okay. So we had, I don't know if it shows you this. It showed me while it was pulling. As soon as I ended, it took it away. But yeah, memorized it. So we have a lot of variation. This is a good one for you to turn and talk to your neighbors about. What direction is the net force on this loop? Alex, you should find people to talk to. Discussion by yourself is kind of not useful. Okay, when you think you have determined your answer, go ahead and answer a second time. And then Abigail will set you all straight. Okay. Abby, you had to answer either one of the bottom 2. Which one did you choose?
I said net force was 0.
Okay, and what was your reasoning?
I said because, the current is going both directions and B is going both directions, so you can't pick one direction for it to go. And if the force equals 0, then the cross product also equals 0. So there can't be a direction.
Okay. I heard her actually explaining earlier, and I heard that part that was the clearest. The current's going both directions. If it's going both directions, when you reverse the direction, when you do the force, you reverse it because the cross product is IL cross B. So current going opposite directions has to add up to 0 if it's the same current in the same magnetic field. Now we can go through and apply this very carefully. You'll notice that it only shows force 2 and force 4. Let's just start with force 1. Force 1 is on the end here. And so using the right hand rule, let's find the direction. What direction should I point my index finger? I should point it that way. So index finger on my right hand is pointing that way. What direction do I need to point my middle finger? It's the same. Well, there's a problem. What's a cross product doing? Multiplying perpendicular parts. What's the angle between those two? 0. What's the sign of 0? 0. So there is no force on that segment 1. That's why it's not shown. Now, if we go to segment 2, doing the same thing, my current is that direction, my magnetic field is that direction, my thumb is pointing in or down, as shown by the arrow. 3, current is that direction, magnetic field's the opposite. What's the angle between those? Technically, it's 180 degrees. The sine of 180 degrees is 0. There's no perpendicular parts. That's 0 force again. And finally, we get to this one. My current is going this direction, magnetic field like that. My thumb is out or up as it's shown in the picture. Now, this was only part 1 of this question. We're going to look at the torque on it in just a moment. But first, a review of torque. Torque, what's the actual equation for torque? Does anyone remember? Yeah, R cross F. It's also a cross product. It's not R times F. It's R cross F, which means we're taking the radius, in this case, the distance from the axis of rotation to where the force acts, times the perpendicular force to that distance. So if I come back and look at this, the axis that it's rotating about is shown. I'm going to put in green. I almost made it. There's the axis it's rotating about. So my R is going to be the perpendicular distance from that axis to where forces are. So for R2, or for 2, there's R2 for force 2, and here's R4 for force 4. Now, if we look at these using R cross F, for force, notice I didn't worry about 1 or 3 because forces were 0. For 2, using the right-hand rule, which finger or which variable is my index finger going to point to for torque is equal to radius cross force? Which one's my index finger, folks? R is my index. So I'm going to start with R2, making my index finger point the direction of R2. Orient my hand so my middle finger can point in the direction of the force. And my thumb points back up the axis. So the torque from R2 is going that direction. Now from R4, what direction does does my index finger need to point? Need to reverse the index finger, also reverse the middle finger, and my thumb again points that way for torque 4. So the forces added up to 0 because the forces were in opposite directions. But because the forces were also on opposite sides, the torque is not 0. So if this motor has a net force of 0 and a net torque that's not 0, what's it going to do? It's going to have an angular acceleration to make it rotate. It doesn't have a linear acceleration. It's not going to travel on me. It's simply going to start rotating. So how do we calculate that torque? Well, the forces were ILB, and A was if we come down here and look again, it defined B as the distance from, let me erase this. B is the distance between two sides of that, and A, I don't see A marked on here. A was the distance in that direction. So that means that A was the length, so just replace L with A, and the force on each of the two sides had a magnitude of IAB. The directions were opposite, that was the magnitude. And then the torques, keep in mind, all of the angles were 90 degrees in my calculation here. The torques were force times 1/2 B, because B was the entire width and it was from the axis of rotation out. So each of those create a torque of, I would have rather put IAB, that's the force, times 1/2 lowercase b. I guess I put it in that order. 1/2 the current times magnetic field times A times B. And now comes something that is not a strict derivation, but turns out to be true. We like to show you simple cases. This was the simple case of a current loop that was rectangular. And if I have a rectangular current loop, then this is the correct equation for, that's the torque due to one side. The torque due to the other side is going to be equal in the same direction. So the total torque is, taking those together, so there's the total torque when I take both sides, but AB is the area of a rectangle. And it turns out that if you do other shapes for the loop, it'll always turn out that you're going to get the area for that term. So this is not a rigorous proof that it's area. It's an example that shows in this case it's area, but it turns out to be rigorously true. So the total torque on that loop is the current going through the loop times the area of the loop times the magnetic field, IAB. Or I like to put the order differently. If I had been the person who originally wrote this, I would have made this IBA for a very simple reason. That's the torque on one loop. What if I had two loops? What would happen to the torque if I had two loops? Two loops, each with the same dimensions and the same current. One loop makes a torque of IBA. So each one alone makes a torque of IBA. If I put the two together, the total torque is the sum of them. So 2 would be 2BA, or 2 IBA. 3 would be 3 IBA. Or if I have n loops, then the total torque is, I put it that way because then I can remember, the NBA. I can remember that. So it's the current times NBA is the total torque on a loop in the magnetic field under, and this is important, under the condition of the geometry that was shown. The geometry that was shown here was that the area, what direction is the area pointing for this loop? I'm going to erase all of my stuff. What direction is the area pointing on this loop? It's a tough question because it's more conceptual. The area, what direction is the area for this tabletop? For a flat surface, we define the vector for the area as the normal direction. So the area of this tabletop is pointing up. The area of this loop is pointing up perpendicular to the magnetic field. So this equation that we found is if the area is perpendicular to the magnetic field. If the area is not perpendicular to the magnetic field, then your torque is going to drop. Such that if we had the area parallel to the magnetic field, if we took that same picture, take the same picture, but we have the loop oriented so it's like this, so the area is in that direction, then I would have the same forces. But how much torque do I make if the forces are one above the other in the same direction? It's not going to make it rotate. That would make zero torque. So it turns out that this equation can be made general by saying the torque is equal to I NBA, and then it'd be sine of the angle between area and magnetic field. So now remember, sine theta will go between +1 and -1. The +1 and -1 is going to indicate, plus and minus will indicate directions. So if I make it go in a full circle, half of that circle is going to have a positive torque, half the circle a negative torque. What happens if I connect a battery up to my simple electric motor here? Starts like this and has a torque that brings it around to here. Torque stops, keeps going, but now the torque is slowing it down and stopping it, and it's going to go like this, which I believe is what I saw somebody doing. It's not going to be a running motor. It's going to be a motor that goes and finally stops here because friction makes it stop. So that's not much of a motor if I put a direct current, a constant voltage on it. There are ways to get around it that we'll talk about in just a moment. So this picture here is showing what if you choose a different angle. So this is showing an angle. Notice the area is this direction here, and the magnetic field, theta, is the angle between the two. And it goes through and calculates, it's going to be torque is equal to I NBA, sine of the angle between them. Something that's very cool, something that we'll be talking about, I think it's the next chapter. A current loop is a magnetic dipole, it turns out. When I have that coil and I have current going through it, it's behaving like a magnet. So we call that an electromagnet. When we talk about Faraday's law of induction, I'll talk about Ørsted and how he discovered this relationship. But for now, it's like we're making an electromagnet by having a loop with current going through it. And then the magnets work to try to make the fields align. So that's another way of understanding how a motor works. So now, question, actually it probably was open for you. Now it's open again. How can an electric motor continue to operate with a DC battery powering it? So this is you looking at those and saying, would that make any sense? Because we haven't talked about the answer. The answer is coming on the next slide. But does that make sense? There are more nerds in the crowd than I anticipated. Especially given my age and your age. I probably shouldn't have said anything because the answers are changing. Don't listen to that man. Okay. Rebecca, Corso, Brandon. It's not? I thought you've been answering earlier. Should I go on? Okay. Unfortunately, erased 112, 2, and 4 were the numbers. Okay. A bunch of people answered this. You studied capacitors. Did we talk about a flux capacitor? You know why? Yeah, only because they don't exist, okay? Great Scott! Another true thing about that movie, which came out when I was in college, which at this point I assume nobody knows anything about. How much power does he need? He says gigawatts. You know why he says gigawatts? No one on the entire set knew how to pronounce that word. And so they just took the best guess at it. And they were wrong, right? It's gigawatts. So shows you just how scientifically accurate things are when nobody even knew how to pronounce gigawatts. See, now they made me do it. Okay, so I didn't put the flux capacitor answer there because that was just a joke. So we had one person that said any electric motor will run off DC power. Okay, sad to say that person wasn't listening because I said won't. By use of a split armature, that is the correct answer. That's where we're going. Of course, you have to know what a split armature is for that to make any sense. And then the last one, there is no way to make a DC motor. Well, I told you, you're just using what you think. It's not something we taught about. So answering number 4, that's acceptable because that's what you think. Answering number A, number 4, D. Number A is not acceptable because I told you that couldn't be it. Okay, so what is the split armature? Here's the idea of the split armature. The split armature has this axle that has 2 pads. One pad covers just a little less than 1/2, and the second pad covers just a little less than 1/2. And then you have brushes. The brushes here look surprisingly like pieces of metal, only because that's what they are. The brushes are pieces of metal that are brushing against that axle as it rotates. And as it rotates, the brush is what's connected to the wires going to the loop. And so you have power coming from your battery that makes this side always positive, this side always negative. And when the brush is touching this, then the blue side is going to be the positive side, and the gray side will be the negative side. Does a half rotation, and the brush is going to switch from one connector to the other one because the connectors are rotating with that axle. And so what that's going to do is switch the direction of the current every 1/2 cycle. So as we talked about, the DC motor doesn't work. It'll go boing and stop because you have torque that goes one direction, then torque that goes the other. But every time you get to the place where the torque is going to switch from one direction to the other, the connectors from positive and negative flip, the current direction flips, and you go to the same current or torque direction again. And so that split armature allows you to keep the torque always going the same direction. And thus you can make your DC motor work. So DC motors, split armature, boom, you're golden. So you can totally make a DC motor. You just have to have a way to switch which side's positive and which side's negative every half rotation. Now, an AC motor. Will an AC motor work? Yeah, because the AC motor is already going to be switching the direction. So an AC motor, you actually can control the frequency of the motor by controlling the frequency of your alternating current, because your current is going to be, one side's positive, one side's negative, and then it switches with the AC. And so it'll just run at the same frequency that you're sending in. So that's a nice way to control the frequency. A DC, you don't have a way to control the frequency. What you can do is control the current. More current's going to give you more torque. It'll go faster before it reaches its final speed. So with a DC motor, the higher the current, the higher the maximum speed. AC motor, assuming you have enough current, the frequency will be the frequency that you're putting in. Okay, we didn't talk about galvanometers when they were in your homework. The galvanometer is now something we can understand better. A galvanometer is created by having a coil here with current, and you put it in a magnetic field. The more current going in that coil, the stronger the magnetic field, the stronger that you create in that galvanometer, the bigger the torque. It's basically like an electric motor, except for it's only going to rotate. You put a spring or something that's going to oppose its rotation, and so the amount it rotates will depend on the amount of torque. And so the galvanometer will tell you then something proportional to, since torque was proportional to current, it will tell you the current by how much it rotates. So galvanometers can be used to measure the current because they're essentially the same thing as a motor. They're obviously much finer design than a motor is. Man. Amperes Law. Now in this class, on the calculus base we did, in the algebra base we didn't. So in the algebra base class, we did not talk about Gauss's law. Gauss's law is a really important law that deals with electric fields. Specifically, Gauss's law relates to a statement that we did talk about in class, that the amount of electric field lines that come out of a charge is proportional to how big the charge is. So remember, we had, if it's twice as much charge, it's going to have twice as many lines coming out. Well, Gauss said, if I take some imaginary surface and I measure how much magnetic field lines are going in and out of that surface, I can then, because of that relationship, tell you exactly how much charge is enclosed. So Gauss's law, spoken in the actual words, says the net flux coming out of a surface, the net flux is the area times the electric field that is parallel to the area, is equal to the charge enclosed divided by epsilon zero, which is just that permittivity of free space. So Gauss's law is a way to relate how much charge is enclosed to how much electric field comes out. Amperes Law, which from now on I'm going to say it like an American would, Amperes Law is similar to that, but it has to do with magnetism. And we really have to talk about Amperes Law, even in the non-calculus based class, because there are things coming up that we can't do without Amperes Law. So Amperes Law talks about a magnetic flux. Well, it's not really flux. It talks about the magnetic flux, kind of. It's really called the circulation. Magnetic flux related to Gauss's law, and Gauss's law told us how much charge is enclosed. There is a Gauss's law for magnetism. That is, the magnetic field lines coming out of a surface will be proportional to the magnetic charge enclosed. But there's a catch. What did we talk about magnetic charges, the north and the south? You never have a magnetic monopole. It's always a dipole. You always have just as much north as you have south, which means no matter what my shape, how much total magnetic charge am I going to enclose? It's always going to be zero because we don't have monopoles. I can't just enclose the north side. I'm always enclosing equal amounts of north and south. And so it turns out that Gauss's law for magnetism says the net flux on any surface is zero because there's never any net magnetic charge enclosed. Hence, we don't talk about that in this class. But we do talk about Amperes law, which is very similar. It's going to talk about what we call the circulation. Circulation is taking a loop. It can be a square loop, a circular loop, we don't care. It's taking a loop and calculating the magnetic field parallel to that loop as you go along the loop. That's called the circulation. So for our purposes, the circulation is the sum over each piece of your loop of the magnetic field parallel to the length of that piece. So if my loop is like this, and my magnetic field is going like, let's say the magnetic field is going like this. If the magnetic field's like that, then it's parallel here, so I would have this length would be delta L1. This magnetic field here is B1. If I go the same direction as the magnetic field, then on that side I would have B1 delta L1. If I go down this way, the angle between my magnetic field and my delta L1 is 90 degrees. How much is parallel? Magnetic field's going this way. Delta L2 is going that way. How much is parallel? 0. So I'm going to have plus 0 for that one. Now if I go this way and I have delta L3, how much is parallel? How much is parallel between the green magnetic field and the blue length? It's all anti-parallel, right? So that's going to put a minus sign because it's anti-parallel instead of parallel. So that's going to be minus B3 delta L3. And then if I come back this way, that's going to be 0 again. So that's how we calculate the circulation. Oftentimes we'll make, for a wire, a circle going around. We'll have a uniform magnetic field everywhere, and you can do things like that. But that's the circulation. And what the circulation tells you about is how much current is going through the loop. Not going through my imaginary red surface, but going through the space in that area. So if I have a wire coming through here, right? If I have a wire that's extending like this, that would be the current that's going through. Now, this law allows us to say current is creating a magnetic field. Now, I told you I was going to talk about Ørsted before I got to this. I was going to have a demonstration. I was sure this wasn't coming up today. I wasn't going to get this far. Was it Hans Christian Ørsted? I think that was his name. He was setting up for, kind of like Hans Christian Andersen, except for no mermaids involved. I saw that mermaid this summer. It's like this big. Just so you know. So he was setting up for a demonstration, and he had a compass like this. I'm halfway to the demonstration. And then he just had an electrical wire going past it to something else. And he turned on the power to the electrical wire going past it, and he saw that his compass rotated. And he was, like any good scientist, what did I just see? Turn off the power, it goes back. Turn on the power, it rotates again. It's repeatable. What's our scientific method? We've been doing that a lot in lab. What's the first step in the scientific method? Observe something interesting. Well, that was interesting. The turning on the power caused the compass to rotate. What's the next step? Make a hypothesis that does 3 things. What are those 3 things? You need to explain why the observation occurred based on scientific ideas and has to make tests that we can predict. And so he said, well, I know that I went from no current in the wire to current in the wire. So it must have been that rotation was caused by the current. And since it's a magnet, the compass, the current must therefore be creating a magnetic field. And so then if the current's creating a magnetic field, then he does there's all kinds of tests that the current's creating a magnetic field. And if I put it in this situation, I can have this reaction and so on, and starts testing. Sure enough, he found that current does make a magnetic field. So anytime you have a wire with a current going through it, it's making a magnetic field. And that's what leads us to Amperes Law, English versus my version of French, which is probably nowhere near actual French. So Amperes Law is what allows us to say, hey, this is how we can calculate the magnetic field that's created by current going through this situation. So this here is just a comparison between the 2 laws, between Gauss's law and Amperes law. One thing that always cracks me up is how do you write Gauss's? SS apostrophe S? As I saw something recent, 2 S's is always enough. You don't need a 3rd S, do you? Also, something that's really important to me, his name was Carl Friedrich Gauss. His name was not Carl Friedrich Gauss or Gauss or anything like that. Because I've heard so many people say Gauss. I had a student once saying he wanted to make a Gauss gun. And I thought he was going to make a gun that shoots Gauss. I was like, why? He meant a Gauss gun. I think his name's Carl Friedrich Gauss. If I'm wrong, well, just color me embarrassed. Point all your friends. Look, here's my teacher being wrong. So Gauss's law had to do with electric field. I told you there is a magnetic version, but we never use it. Ampere's law has to do with magnetic field. Gauss's law applies to closed surfaces, three-dimensional surface that was closed. Ampere's law is a closed path. Your loop has to come back on itself, just like an electric circuit. Gauss's law related charge enclosed with electric field flux or electric field strength. Ampere's law is the current flowing with the magnetic field. Gauss's law dealt with the perpendicular electric field. Ampere's with the parallel magnetic field. And then you had the circulation versus the flux. So we're going to get right to the last thing we'll do today. The magnetic field created by current going through a wire. If I have current through a wire, there really are only two options for the magnetic field symmetry. What's the rules we learned? Let's start with electric field. What's the rules we learned with electric field in regard to the electric field lines and charges? Electric field lines went out of positive and into negative. For magnetic field lines, what did we learn about the magnetic field lines and the charges, which are north and south for magnetic? No, the magnetic field lines for magnetism. Did I say electric?
No.
Okay, magnetic field lines go out of north and into south. But there was one clear difference. Those things sound pretty much the same. Electric field lines start and end at charges. Magnetic field lines always do loops. They don't start and end. So because the magnetic field lines always do loops, the only symmetry that's available for a wire carrying current would be if it makes magnetic field lines that do circular loops around the wire. That's the only symmetry that can abide by, or the only shape that can abide by a symmetrical wire and making loops. Right? You can't have loops if they're starting at the wire or ending at the wire. So you have to have loops that are either clockwise or counterclockwise. And this will be the last thing I say because I only have 1 minute. We use the right-hand rule, once again, the right-hand rule, but in a completely different form to determine the relationship between current and magnetic field lines. So the right-hand rule for a current-carrying wire. You take the wire and you put your thumb along the wire so it's parallel to the current. So if the current's going up, my thumb points up. Of which hand?
Right.
Right. Then I just wrap my fingers around the wire. At any point, the magnetic field is going the direction that my fingertips are pointing. So if I want to know what direction is the magnetic field in the direction of Abigail from this wire, I'll orient my hands and my fingertips are, between the wire and Abigail, and the tips of my fingers are pointing this way, so the magnetic field's going that direction. If I want to know at, now my brain goes, Amanda's location, then I put so the tips of my fingers are between the wire and Amanda, and it's going this direction. And so I can determine the direction of the magnetic field going in circles around by using that right-hand rule. Thumb in the direction of the current, fingers wrapping around the wire. Put the tips between the wire and the place you want to find the direction of the magnetic field. The direction the fingertips are pointing is the direction of the magnetic field.